Hello and welcome to the next part of the Further Maths Support Programme core revision sessions. Today we're going to be looking at a little bit more A2 differentiation. This is the second part of A2 differentiation that we're going to be doing. So far in a previous video we've covered chain rule and product and quotient rules. Today we're going to take a look at exponentials and logarithms. There's going to be a little bit of enrichment nugget after that, and then we're going to do the trigonometric functions. All of the material that we're going to be covering today is in C3, Core 3 for all four of the main specifications. Okay, so let's make a start. Things that you need to know on exponentials and logarithms. So first of all, I just want to pick up here on the basics that you need for this particular topic. Sorry, let me just get my pen up and running. Okay, so if you are given a function of the form y equals a e to the bx, when you differentiate that, you're using the chain rule to differentiate. That was revised in the previous video. Just notice when you differentiate using the chain rule, you differentiate the outside function, that's the e to the something, and you multiply by the derivative of the inside function, that's the bx, the derivative of that is b, so differentiating e to the bx becomes b e to the bx, and the a that was the coefficient in the original expression for y is completely unchanged, it just stays in exactly the same place. If you're differentiating then y equals log ax plus b, the derivative there is dy dx is a over ax plus b. Again, this is using the chain rule. Differentiating the logarithm gives you a reciprocal, so the derivative of log ax plus b gives you the 1 over ax plus b here, and then you need to multiply by the derivative of the inside function, that's the derivative of ax plus b, which is just a. Do you just need to be a little bit careful in a special case of differentiating logarithms? A classic example would be y equals the log of 3x. When you differentiate this using the chain rule method that we were just talking about, you end up with 1 over 3x from differentiating the logarithm, and you multiply by 3 from the chain rule, that's differentiating the inside function, the 3x, that differentiates to 3. So you can see that that cancels to 1 over x. That may feel a little bit odd in that the derivative has no effect from the 3 that's in the original expression. An alternative way of thinking about it is that you can actually expand that logarithm. If y is equal to log 3x, that's the same as log 3 plus log x. Check your logarithm rules from your AS core, and then when you differentiate that, log 3 here is just a constant, so it disappears when you differentiate, leaving you just differentiating the log x, which is 1 over x, as we expected from our previous method. So do just watch out for that. If, however, you're going to differentiate something like y equals log of 5 minus 2x, in here, differentiating the logarithm gives you 1 over 5 minus 2x. Differentiating the inside function gives you negative 2. So your overall derivative there, minus 2 over 5 minus 2x. And that negative 2 can't cancel away because of this constant value 5 in the denominator. There's no common factor of minus 2 in the numerator and the denominator to cancel out, as there was in this example up here. Okay, so let's take a look at some examples here. All the way through this video we're going to be using these multi-choice questions, so if at any point you want to stop the recording, have a little go at the question yourself, by all means do. I'm going to keep going and work through the explanation for this one, but you can restart the recording if you want to when you're ready to hear that explanation. I'm just going to change my pen colour because I'm being fussy. Okay, derivative of e to the minus 3x then, so we're differentiating with respect to x, e to the minus 3x. Differentiating the exponential leaves the expression apparently unchanged, so e to the minus 3x, multiplied by the derivative of the inside function, so that's the derivative of minus 3x, and then we can find the product of those two, so minus 3e to minus 3x. I think that comes out matching answer C here. I hope that makes sense. Differentiating log 2 minus 3x is very similar to the example we did just now. So chain rule derivative here, differentiating the logarithm gives you a reciprocal 1 over 2 minus 3x, and you multiply by the derivative of the bracket, which is minus 3, and simplify to minus 3 over 2 minus 3x. So that's found an expression for dy by dx. So the gradient at the point where x is 0 is going to be minus 3 over 2 minus 0, so minus 3 over 2, and I think that matches quite nicely here with answer D. Okay, slightly more complex version in here. This is actually harking back to the product and quotient rule topic that we were just talking about in the previous recording. So we have here an expression that has two functions multiplied together. We have an exponential function at the beginning, and we have a logarithm function at the end there. I'm going to call that first function u and the second one v, and I'm going to say then that d by dx of my function e to the x log 1 minus 2x with respect to x here is going to be, right, so v is log 1 minus 2x. du dx, I'm now going to differentiate my e to the minus 2x, and using my chain rule that gives me minus 2e to the minus 2x. I'm going to add to that the product of u, which is e to the minus 2x, and dv dx here is going to be negative 2 over 1 minus 2x. That's the logarithm differentiating to 1 over 1 over 1 minus 2x, and the bracket there, the derivative of that is negative 2. So we can do some simplifying here. Let's just tidy this all up a little bit. I make that minus 2e to the minus 2x log 1 minus 2x minus another 2e to the minus 2x over 1 minus 2x. And I think we could take a factor out of there to start to make it look more like the answers at the top. So minus 2e to the minus 2x appears in both expressions, leaving us inside with log 1 minus 2x minus 1 over 1 minus 2x. Let's see if we can match that up with one of the expressions at the top here. We know it's not A, we know it's not D. All we need to do is make sure we get the correct sign in the bracket. I think that this should therefore be answer C. I think that's the one that gives us the best match. Okay, so here we've got a little practical application of the exponential functions that we've been looking at. The size p in thousands of a population of bacteria after t hours, some of these examples can be pretty gross, is modelled by p equals 3e to the 0.12t. And we have to decide the rate at which p is increasing after 2 hours. Now, as soon as you see the word rate, you know that you're going to be differentiating, and in this case we're looking at the rate of increase of p, so we know that we're going to be looking for dp dt, the derivative of p with respect to time, the rate of change of p with respect to time. So let's differentiate our expression that we've got up here. Let's just leave our 3 out at the front for the time being. Differentiating e to the 0.12t gives us e to the 0.12t, that's differentiating the exponential, and then we multiply by the derivative of the bracket, that's the 0.12t, so we just multiply by 0.12. That's going to simplify down to 0.36 e to the 0.12t, and then we're going to need a little calculator handy. So we've got at time t equals 2, we've got dp dt, sorry for my poor notation here, dp dt is going to be 0.36 e to the 0.12 times 2, and I'm just going to tap that straight into my calculator here, so that gives me 0.36 times, I'm going to use my exponential function on my calculator here, 0.12 times 2, and that gives me 0.458, I think, to 3 significant figures, straight out of my calculator there. So 0.458 thousandths of bacteria per hour. There we go, that matches nicely with answer A there. Okay, so a little nugget of enrichment on differentiation. I want to just have a little think about what these two videos have in common. They're only very short, but just bear with me. I will just going to switch screens to take a look at those. Bear with me a moment. Okay, so I can't get the right one to come up. Okay.
Bacteria reproduce very simply and rapidly by doubling their contents and splitting in two. Just one bacterium, dividing every 20 minutes, could produce nearly 5,000 billion bacteria in one day.
Okay, so we were just talking about bacteria a moment ago. I'm going to switch to a slightly different program. Just bear with me a moment. My screen switch is not working currently. Okay, let's have the second one up for you. Okay, this one may seem unfamiliar to start off with, but I'm sure you'll recognise it in just a moment.
Con los terroristas.
Those of you that haven't met the Harlem Shake before, what planet have you been on?
Do the Harlem Shake.
Perhaps a version that you haven't seen before this time. Okay, so let's switch back to our presentation here. Again, bear with me, I'm having a little issue with my screen switch. Okay, so I was interested to know what you think these two videos have in common. So I wanted to show you this little graph here. This is a graph that I googled. It shows the search popularity for Harlem Shake videos. So looks at when people were searching based on Harlem Shake, and you can see here right at the beginning of 2013, just at the end of January here, the video was released as a part of a compilation, and its growth just grew and grew and grew and increased, and we're going up here to kind of mid-February 2013. And I think you can probably see from the graph here that it's fairly reasonable to use, I would suggest, an exponential growth rate as a model for the popularity, the search popularity for Harlem Shake. I just wanted to compare and contrast that with a bacteria population growth curve. Sorry, this is a little bit on the fuzzy side, but we have a very similar type growth going on with bacteria. You start with this sort of slow phase at the beginning here, where not very much happens for a long time, and then all of a sudden that internet meme becomes popular, and its word starts to spread about it. People will share it and increase its growth even further. Now there's an interesting little change at the top here in this graph that didn't appear in the Harlem Shake graph. Now what this suggests in the case of the bacteria growth is that the bacteria eventually come to a point where they run out of food, and they stop growing, and eventually they will decline and die off. And that, for me, raises the question whether exactly the same model applies to the internet meme as well, whether the Harlem Shake, you know, will come to a point where people stop feeding it by sharing it, and eventually it will die away and become less popular. If I've accidentally become the person that makes it stay alive for a little bit longer, then I kind of apologise on that front, but there we go. Don't feed it and it'll die away. Right, onwards then let's have a little look at trigonometric functions. So some standards here. These are the ones that you'll need for your A2 differentiation techniques. You need to know how to differentiate sine. Sine differentiates to cosine. Cosine differentiates to negative sine. Just notice the sign change there. That's really important, and that's probably the part of this topic that causes people more difficulties than anything else. The tan function here differentiates to sec squared, and I think most of you will have seen a little proof of that done in lessons using the quotient rule, but let's just very quickly look at that. If y equals tan x, that can be written as sine x divided by cosine x using a classic trig identity. If we want to differentiate that, dy by dx. We treat the numerator here, the sine x is u, and the denominator as v, and using our quotient rule formula, v du dx minus u dv dx all over v squared, we can work that through. So starting with v, and then du dx, so the derivative of sine x is cos x, minus u is sine x, and the derivative of cosine x, so this is dv dx, is negative sine x, and that's all over v squared, which is cos squared x. It's looking a little bit on the complicated side at the moment, but we can simplify that numerator to cos squared x plus, because we've got a negative and another negative, plus sine squared x all over cos squared x. The numerator, as you know from another trig identity, is the same as 1, so 1 over cosine squared x, and you can see that that simplifies to sec squared x. Okay, so that's just a little justification for you for the tan derivative being sec squared. Can I just, if you haven't already noticed this, I'm just going to point it out as clearly as I can. All of these differentiation methods only work if your angles are given in radians. The derivative is not valid if you're working in degrees. So where your maths teacher will have been nagging you and nagging you and nagging you to learn how to work in radians, alright, this is the point where it becomes absolutely crucial. You won't be able to use any of these derivatives if you're working in degrees. Okay, let's take a little look at some examples on this one. So being asked to find the gradient of the curve y equals tan 2x at the point with x coordinate 0. So we're looking to find the gradient function dy dx. And we can do this using chain rule. Tan 2x is a composite function, the tan function on the outside and the 2x on the inside. So differentiating the tan part gives me sec squared 2x. Differentiating the 2x part gives me 2. So that becomes 2 sec squared 2x. We want the gradient when x equals 2. When x equals 0. So the gradient is going to be 2 sec squared of 0. Well, sec squared is 1 over cos squared, so we've got 2 over cos squared 0, and cosine of 0 is 1, so this is 2 over 1 squared, which is 2. Okay, so our gradient of our curve at that particular point here is going to be 2. Okay, derivative of log sine x, again we've got a composite function. These composite functions keep coming on over and over and over. This is why the chain rule is so crucially important. Okay, another composite function, the logarithm is the outside function, the sine x is the inside function. So when we differentiate d by dx of log of sine x, if we differentiate the outside function first, we get 1 over whatever's inside the bracket of the logarithm, so 1 over sine x. We multiply by the derivative of the inside function. Derivative of sine x is cosine x, so we end up with cos x over sine x, which is 1 over tan x, or cot x in this case. So again, answer A is the best answer for this particular question. We've then got sec 2x in this case, and we've got to find dy by dx. There are some standard derivatives for sec and cosec and cot. We're going to work this through using a little bit of chain rule. If we know that y equals sec 2x, we know that that's the same as 1 over cos 2x. We can either do this using quotient rule, or we can use a little bit of just chain rule on its own. I'm going to use the chain rule here. I'm going to rewrite that as cos 2x to the power of minus 1. Just be a little bit careful here. Cos squared 2x is the same as cos 2x all squared, but cos negative 1 of 2x has a different meaning to 1 over cos 2x. We do have to be a little bit cautious because there's this complication of meaning in that that -1 there, it technically means the inverse of the cosine there, so we just need to be a little bit cautious with the notation that we use at this stage. I'm just going to leave the -1 outside the bracket there anyway. So when I differentiate using chain rule, differentiate the outside function, I get -1 cos 2x to the -2, that's putting the power in front and reducing the power by 1. I've then got to multiply by the derivative of the bracket. I'm going to use a little bit of chain rule here again. Actually, this is going to be when we differentiate the cosine, we get negative sine. We're also going to need to multiply, excuse me, running out of space here, by another factor of 2, so that our dy by dx, let me give myself a bit more room over here, dy dx, we've got two negatives multiplied together. I make that 2 sine 2x all over all over cos 2x to the cos 2x to the 2. That doesn't quite yet match up with any of the answers that we've got on the screen, so let's combine our sine 2x with one of the cos 2x's. I'm going to make that 2 tan 2x, and then we've got a remaining cos 2x in the denominator. I'm just going to write that as sec 2x in the numerator, and I think that should then match up with answer D. That's our best answer. In this case, we've got the 2, we've got the tan 2x, and we've got the sec 2x. Okay, so that brings us to a close in this session today. If you're interested in details of any other online or face-to-face revision events, or for any of our other enrichment or CPD activities, or for any advice on further maths or maths A-level, you can go and have a look at www.furthermaths.org.uk. You should be able to find lots of information in there that will help you out. You're also able at that site to go to your local area if you're in England, and find your local contact for the Further Maths Support Programme, who'll be able to offer further advice if you need it. I hope you've enjoyed the session, and do feel free to go ahead and find some of the other recordings that are available as well. Bye!